We left you on Friday with a problem that amounts to a mathematical application of this law that we call Newton's third law. Remember, at this point, we have three laws of Newton's, three very important, seemingly different, but at some level intricately related laws. First one says an object at rest stays at rest. An object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. Newton's first law, sometimes called the law of inertia. The second law says the acceleration of an object is directly related to and in the same direction as the net force, and it's inversely related to the mass. Bigger the force, bigger the acceleration. Bigger the mass, smaller the acceleration. The third law says if object A applies a force on object B, then object B will apply an equal and opposite force on object A. That's the law. Now, mathematically, okay, that has some implications as well. That means, for instance, if two toddlers get in an argument and push each other, we get a 15-kilogram toddler or a 20-kilogram toddler in this case, then they will push each other every single time with the same force in opposite direction. So let's say the 15-kilogram toddler pushes a 20-kilogram toddler. You can say, hey, wait, no, the 15-kilogram toddler could push hard, could push harder than the 20-kilogram toddler would push. No, he can't. Because in the end, if the 15-kilogram toddler pushes harder, then the 20-kilogram toddler will push harder back. It's a law of nature. It has to be that way. Okay? So that's why this problem that we're seeing here is an application of this Newton's third law. This guy applies a force on this guy. Call this object number 2, object number 1. Guy number 1 or kid number 1 pushes kid number 2. They apply equal and opposite forces. Kid number 2 accelerates at 1.5 meters per second squared. We want to know how fast the 15-kilogram toddler, toddler number 1, is moving. Let's write down some givens here. First, for toddler number 1, his mass or her mass is 15 kilograms. Let's say mass number 2 is 20 kilograms. Let's say that acceleration number 2 is 1.5 meters per second squared because that's what we're told. We want to find the final speed of the first toddler. And finally, we know that that toddler number 1 pushes on number 2 for 0.55 seconds. Hey, wait. Or is it toddler number 2 pushes on 1 for 0.55 seconds? Which one is it? Which one pushes for 0.55 seconds? Toddler number 1, right? Or could we just say delta t separate from number 1 or number 2 is 0.55 seconds? If no one pushes on the other for 0.55, isn't the other pushing on the first for 0.55? Yeah, if object A applies a force on object B, then one of those forces can't disappear sooner than the other force. It's got to be 0.5 for both of them. So we got a couple of options here. We can find F2 by saying M2 times A2, and then plug that into this equation for acceleration of the first object, okay? Making sure we recognize that those two forces are the same value. Or we can just set them equal to each other right off the top. Say F1 equal to F2. Is that right? Almost here. What's wrong? Michael? Yeah. Doesn't matter which one you make negative. They're equal and opposite. Which one's negative? Who cares? One's positive, one's negative. All right, now let's say M1A1 equals negative M2A2. M1, 15. A1 don't know. Negative 20 times 1.5. That's going to give me 2, I think. Negative 2.0. Hey, that's not what I'm looking for, though, is it? I don't want to know what A is. Why did I find A? 3 words. Because I could. That's why I found A. Because I could. You may, when you read this question, have this insight that tells you, oh, okay, I got to find acceleration and use acceleration to find the final speed. You may have that insight. You may not. That's okay. Either way. If you don't have that insight, then get something. I just got something. Is that helpful to me? Yeah, probably. But if it's not helpful to me, it's not a big deal because it's not wrong. Is this helpful to me now? Am I going to be able to use that to find final speed, Merrick? How? Good. Say A is equal to delta V over delta T. There it goes again. Delta V, we're looking for delta V here. It's A times T. We get an acceleration of 2.0 or negative 2.0 meters per second squared times 0.55 seconds. That's going to give me 1.1 or negative 1.1 meters per second squared, meters per second. 2 digits, because if we go back here, everything's 2 digits, right? Final answer should be 2 digits. Hey, a couple of questions for you right now. First of all, why is that a negative value? Should it be? Should it be negative? Sophie, should that be a negative value? Yeah, how come? Why should it be negative? No, Alice, help her out. Right. If the first velocity, we're not told that the first velocity is positive, but we made the first acceleration positive. So the second acceleration velocity should be negative. It's the opposite direction. Okay, good. Second question is, we get a value of 1.1 meters per second squared. Let's not pay attention to that for a second. Okay, let's look at the acceleration of the second object, or the first object, I should say, negative 2. It's a bigger value than the acceleration of the 20 kilogram toddler. Should it be? Elizabeth, should this acceleration 2.0 be bigger than 1.5? Yeah. Why? Because the mass is smaller. Good. A bigger acceleration, same force, bigger acceleration, okay, because it has a smaller mass. Right? You guys good at those? Okay, we're going to shift gears a little bit, kind of. We're going to go from Newton's third law to looking at a bunch of applications of force problems now. Over the next couple of days, we'll do several different applications, problems which really you could have done before, but now that we have a little bit more background, you're a little bit better equipped to solve now. Okay, at some point over the next couple of days, we'll actually integrate those multi-force problems, F net is equal to the sum of the forces, with a little bit of Newton's third law that we talked about over the last couple of days. For now, let's just do a few more of those F net is equal to the sum of the forces problems. They're going to look different, but they're going to boil down to something that is pretty much the same thing as what you've done. Unfortunately, the first one we've got to do isn't in our textbook, so you're going to have to copy this one out. This one says a 73 kilogram man stands in an elevator that accelerates downward at a rate of 2.0 meters per second squared. You know, in Physics 20, we don't encounter this nearly as often as we do in Physics 30, but we still do see it, and we should pay a little bit more attention to this. Okay, in Physics 30, I always tell my students to take a red pen and circle anything in a question to draw attention to it if it's something that can lead you to a silly mistake. Like, for instance, this downward acceleration. Why might that lead me to a silly mistake? What might I miss if I don't draw attention to that, if I don't circle it in red or highlight it in pink or something? Yeah, it's got to be a negative acceleration, right? Negative 2.0 meters per second squared. They don't tell me in the question it's negative, but they do tell me in the question it's negative. I just got to read between the lines. Okay, I recognize that, but if I don't draw attention to it, by the time I'm finished reading the question, I might just forget. I got to write down my givens. So we want to find the force of the elevator floor pushing up on him. We want to find the man's weight, his real weight. We want to find the normal force acting up on him, and we want to find his apparent weight, how heavy he actually feels here. Not how heavy he is, but how heavy he feels. There is more than one force acting on this guy in the elevator. If there was just one force, Clearly it would be gravity. We know gravity acts on the guy, right? Acts on everybody on the Earth. If it was just the force of gravity, what would happen to him? No, if it was just the force of, well, actually, you know what? If it was just the force of gravity, he would appear weightless for a brief time, for a second or two, until he went splat on the ground, because he'd be falling, free falling, and as he's free falling, he would be weightless. It just wouldn't last for that long, right? Because he'd hit the ground. Right? So if it's just gravity, he free falls downward until he hits the ground. So it's clearly not just gravity, right? Although the gravity's there, it's not just gravity. What other force acts on this guy? What other force acts on this guy? I'll give you a hint. What's the hint? Jonathan? Yeah, the force of the floor pushing up on him, right? Now, is the force of the floor pushing up on him bigger, or is it smaller than gravity? How do you know? Good. Not because he's going down, but because he's accelerating down, right? He could be going down, but be slowing down. In that case, normal force would be bigger. But since he's accelerating downward, we're going to say that normal force is smaller than the force of gravity. All right, that's it. At least hopefully that's it. Unless this elevator is swinging in the wind from side to side, there are no other forces acting on the elevator here. So let's say F net is equal to the sum of the forces. That's Fn plus Fg. Ma is equal to Fn plus Fg as well. And the mass, plug in your numbers here. 73 kilograms to the mass. Fn is, oh wait, we know the acceleration, right? 2.0. Fn is what we're looking for here, the force of the floor, plus 73 times negative 9.81, because gravity is acting down. Is that right? Caitlin? With what? Yeah, right. That's why we circled that, right? To remind us that the acceleration is going to be a negative value, that it's a downward acceleration. Good. So 73 times negative 2 gives me negative 146. 73 times 9.81 gives me 716.13 newtons, which we're going to take the other side by adding. And we get Fn equal to 570.13 newtons. Now, we're going to record that up here as 2 digits, 5.7 times 10 to the 2 newtons, because, of course, look back at this, 2 digits, final answer should be 2 digits. The floor pushes up with 570. Gravity pulls you down harder, but the floor still has to push you up, otherwise you'd free fall downwards at 9.81 meters per second squared. What about the man's actual weight? Do you remember, Olivia, do you remember how we defined actual weight way back on, I don't remember what day it was, last Tuesday maybe? We talked about 3 different types of forces. No, it was before that. 3 different kinds of forces. One was the weight, one was the normal force, and one was the force of friction. Do you remember how we defined weight? No? Nick, do you remember how we defined weight?
9.81 times.
All right, so force of gravity. Right? Force of gravity, 9.81 times the mass. If we want to find the man's actual weight, all we're going to do is say m times g. Now, please, when you see this question on your unit test or your final exam, and I promise you, you'll see it in one of the 2 places, the unit test or the final exam. What's the weight of somebody? It is not 73 kilograms. That's the mass. The weight is, as Nick said, mass times 9.81. 73 times 9.81 gives me 716.13 newtons, or we should round that to 7.2 times 10 to the 2 newtons. Guys, look at that. I used 2 digits, I used 3 digits, final answer should be 2. Mass is 73. If I ask you for weight, don't say it's 73. It isn't. The weight is 7.2 times 10 to the 2. All right, next. What's the normal force acting on this guy? Oh, don't make this harder than it has to be, please. What's the normal force acting on this guy? What's the normal force defined as? The force of the... What is it? Yeah, it's the force, in this case, of the elevator floor acting up. Yeah, it's 5.7 times 10 to the 2 newtons. Right? No new calculation to do there. It's the same thing. We've already done it. Don't do it again. Finally, what about the apparent weight? How heavy he feels. Grace? It's exactly the same thing. Good. Okay. Apparent weight is defined as the normal force. So he is 716 newtons, or 7.2 times 10 to the 2 newtons heavy. He feels lighter. Why does he feel lighter? You guys have all experienced this. You're in an elevator. It starts going downward. It accelerates downward pretty quickly in the beginning, at least. Your throat goes in, or sorry, your heart goes into your throat, or your stomach goes into your throat. It feels like it. You go over like a bump on a roller coaster like this. You feel like your stomach is going into your throat, right? Why? Because you're accelerating downward. As you accelerate downward, you are lighter. You feel lighter than you really are. Okay, that's why your stomach goes into your throat. You feel lighter than you really are. That's what's happening here. He is 7.2 times 10 to the 2 newtons heavy. He feels 5.7 times 10 to the 2 newtons heavy. I'll get another example for you, and then we'll give you some time to work on some questions here. Similar, but not the same. This time we got a person in an elevator, but this time we have the combined mass of the person in the elevator. Here it is. 600 kilograms. There's a force of the elevator cable acting up. We could call that Fn if we want, because it's like the elevator floor pushing on the person, except it's acting on the entire elevator. I'm going to call it Fc for the force of the cable. Okay, if you want to call it Fy for the Y component, go ahead. Dom just asked a good question. Hey, I said call it anything you want, right? Dom said, could you call it FF? You call it FF if you want right here. But if friction's involved in that other question, no, you don't want to call it FF, right? Because you don't want to have two forces named the same thing. Call it whatever you want, as long as you haven't called something else the same thing. We wouldn't want to call it FG here, because we're going to have a force of gravity here. Yeah. We do have a force of gravity here. Oh, let's label what this value is, actually. 6.50 times 10 to the 3. We do have a force of gravity here. It's acting down. I want you to yell stop when my force of gravity is the proper length, or at least approximately the proper length. That's pretty short. Do you know what? We don't know how long the force of gravity is. It's a bit of a trick question. Draw it any length you want in this case. Why? Because we're not given any indication which one's bigger. It's accelerating. Is it accelerating up or down? We don't know. So, Nick, you said stop pretty quick there. Needed to be, I think, kind of funny. Trying to be funny. Kinda.
Funny guy. Yeah, I noticed.
But you know what, Nick? Like it would have been okay. Like you had it drawn it that way, I wouldn't mark that wrong. Okay, somebody else draws it twice as long as I have, I wouldn't mark that wrong, because in the end, we just don't know. So draw it any length you want. You can't get marks taken off for drawing it the wrong length. Let's say F net is equal to the sum of the forces, Fc plus Fg, which is the same thing as Fn plus Fg, right? M is 600. This time, remember, it's the mass of the elevator and the guy inside. Should we draw the guy inside? Should we know his mass? Should we know whether he's moving or not in the elevator? Should we know whether he's smiling or breathing or... Does it matter? No, it doesn't matter in the slightest. It doesn't matter in the slightest whether the guy is moving or what his mass is, as long as the mass of this elevator includes the mass of the guy. It doesn't matter in the slightest. I had, when I was a kid, I had an uncle who lived in Ontario. I grew up in Nova Scotia. Okay, I had an uncle that lived in Ontario, drove a semi-truck for a living, delivered ice cream. And every once in a while, it was maybe once a year, once every couple of years, he would make a delivery. He would get the delivery to the East Coast. So he would take a semi-truck full of ice cream to Halifax from Toronto and drop off this load of ice cream in a warehouse somewhere in Halifax. And whenever he did that, every year or year and a half or so, he would stop when he got to my grandfather's house, spend the night there instead of sleeping in the sleeper of his truck. He would sleep in a bed at my grandfather's house, and we would go visit him because we never get to see him. We get to see him once every year and a half or so. And I remember this one time we went out to visit him at my grandfather's house, and we're excited to see him, but we got even more excited when he told us he had a little surprise for us. Turns out, somewhere between Toronto and Truro, Nova Scotia, where my grandfather lived, a pallet of ice cream had shifted and tipped over in the truck, and it dented the corners of all these boxes of ice cream. And he called his boss in Toronto and said, "Well, what do I do with it?" Boss said, "Well, basically can't sell it. The corners of these ice creams are dented, so you can't sell this ice cream. So just leave it. Just leave it wherever you are." So we got a pallet of ice cream for free with dented corners. That's it. It was great. But you know what? Normally that doesn't happen, right? Normally the pallet of ice cream doesn't tip over in the truck. Normally the motion of the ice cream inside the truck is exactly the same as the motion of the truck itself. But even when it isn't, even when the ice cream does tip over in the back of the truck, does the motion of the ice cream within the truck affect the truck itself? If we were analyzing the motion of the truck, would we pay any attention to the fact that the ice cream tipped over inside? No. So we don't care about the guy inside this elevator either. If we're analyzing, as we did in this last question, the guy, the motion of the man, okay, that matters. Just like if we're analyzing the motion of the pallet of ice cream. But if we're analyzing the truck, or in this case, the elevator, then what's inside it makes no difference as long as we're accounting for its mass. Does that make sense? All right, 600 kilograms for the mass of the ice cream and the truck, or in this case, the guy in the elevator, times the acceleration equals FC, which is 6.50 times 10 to the 3 newtons, plus, what do we got here? 600 times negative 9.81 meters per second squared. Let's get this as a class. Okay, let's say 600 times negative 9.81, first of all. Okay, now let's add that to 6,500. Now let's divide that by 600. And I get 1.02 meters per second squared. 3 digits, right? 3 digits, 3 digits, 3 digits. What have I just found technically? Well, I found the motion of the elevator, right? The acceleration of the elevator. Assuming the guy, though, isn't jumping around in the elevator, what's his acceleration? Assuming the pallet of ice cream in the truck isn't falling over, then what's the acceleration of the ice cream pallet? Same as the acceleration of the truck, right? What's the acceleration of the guy inside this elevator? Same as the acceleration of the elevator, 1.02 meters per second squared, assuming he's not doing anything strange like falling over inside it. right? Good there? Okay, let's take a few minutes and take a look at those two questions, please, on page 152. All right, taking a look at number 2, it says an electric chain hoist in a garage exerts a force of 2850 newtons upwards on an engine. We're going to make this our engine. It's going to be a conveniently very square engine. It experiences a force upward. We're going to call it Fc for the force of the chain of 2.85 times 10 to the 3 newtons. Don made a good point last time. He said we wouldn't want to call it FF if there was a force of friction there, right? Next unit, we actually do something called centripetal force. It's a force of an object going around in a circle. We're going to call that Fc. In that situation, we probably wouldn't want to call this Fc either, right? Because we don't want to call two different forces the same thing. But right now, Fc is fine. Right now, FF would be fine as well. Although it would have no significance to this question, it would still be okay. Got that force upwards. We know the acceleration of the engine is upwards. So it's going to be positive 1.50 meters per second squared. We want to find the mass of the engine. What other force acts here? What other force acts here? We know this, right? Easy. What other force is it? Gravity. Do we know whether it's bigger or smaller than the upward force? Oh, but we do. In this case, we do. Okay, we know whether we should draw it longer or shorter or the same length as the upward force of the chain. So do you know which it is? Longer, shorter, same length? For gravity. No? Matt? Shorter? Why would you say shorter?
Because there's the force is greater.
Okay, how do you know the force is greater going up? Good. It's upward acceleration, so that upward force has to be greater. Therefore, force of gravity. How much smaller is it? I don't know exactly, but we know it's smaller. All right, let's say F net is equal to the sum of the forces. In this case, it's going to be Fc plus Fg. We're going to say M times A is equal to Fc plus Fg. Mass here was 2.85 times 10 to the 3. The acceleration here is 1.5. Oh, wait. It's not 2.85 times 10 to the 3, is it? We don't know the mass, do we? We don't know what the mass is. That's what we're trying to find. The acceleration is 1.5. The force of the chain is 2.85 times 10 to the 3. And the force of gravity is m times negative 9.81. Here's where the problem arose. We were trying to find mass. Although it's only one variable that we're looking for, it's in two places. Let me ask you 3 questions to kind of lead you into solving this. What is 1 apple plus 2 apples? You're trying to add apples here. Okay, you're a little kid. Okay, you're in kindergarten maybe. They're trying to teach you how to add, and they get these manipulatives out on the table, apples. They got 1 apple over here, they got 2 apples over here, and they say, okay, little Johnny, what's 1 apple plus, get a Johnny because it's Johnny Apples, see, 1 apple plus 2 apples. What's the answer to that question? Andrew? 3 apples, good. Ask Leandro because he's smart, and I knew you'd know the answer to that question, right? 1 apple plus 2 apples is equal to 3 apples. Leandro, you could go back to kindergarten and ace it without even studying at all. That's how good you are. What is 1 apple plus 2 apples is equal to 3 apples, and what's 1x plus 2x? What's 1x plus 2x? Let's see here. Who haven't I called on today? Phil, what's 1x plus 2x? 3x, good. Dane, what's 1m plus 2m? Good. 1 anything plus 2 anything is 3 anything, right? All right, so let's say 1.5m plus 9.81m, right? We're taking 9.81m over to the other side by adding. It's the same thing as saying 1.5m plus 9.81m. We know how to solve that. Everybody I asked a question to in the last minute. Okay, 1 apple plus 2 apples, 1x plus 2x, 1m plus 2m, all said 3, right? 3 apples, 3x, 3m. What's 1.5m plus 9.81m? Add the two numbers together. We get 11.31m. It's the same as you added 1 plus 2. M's are apples. Okay, take it to the other side by adding. 1.5 apples plus 9.81 apples equals 11.31 apples. Now we're going to take this over, so 11.31 over by dividing, and when we do that, M works out to be 252 kilograms. Should be 3 digits, because if you go back to your original data, 3 digits, and then of course the 9.81 is also 3 digits. Good? Let's try another one then. More problems. This one says a skydiver is jumping out of an airplane. During the first few seconds of one jump, the parachute is unopened, which is what you want, right? First of all, you don't want the parachute to open right away and get the parachute caught up in the airplane. Okay? You don't want to be dragged behind an airplane. Second of all, what fun is it if you don't free fall? And as long as the parachute is out, you're not going to free fall. So you want to free fall for a few seconds before you pull that parachute. Okay, you want to experience weightlessness before you pull the ripcord so that you open the parachute. At one moment in time, as this parachute or as this skydiver dives, we're going to draw him upside down because if he was like this, he wouldn't really be diving, would he? He'd just be jumping, sky jumping. Here he's diving. I don't care how you draw him. At one moment in time, he's got a force of air resistance acting up of 250 newtons. 1 second before that, it would have been different. 1 second after that, it would have been different. Air resistance is unlike friction. It depends upon how fast you're going. Friction, hey, once you're moving, force of friction is the same no matter what. Air resistance, not so. You ever try holding up a piece of plywood? Hey, walking with a piece of plywood like this? You can do it, right? You ever try holding up a piece of plywood like this when you're standing in the back of a truck that's moving at 100 kilometers per hour? It's impossible because the force of air resistance is much bigger when you go faster. Friction is not like that. Air resistance is. At this one moment in time, air resistance is 250. At this one moment in time, the acceleration is downward at 5.96 meters per second squared. Gravity acts down. Gravity is smaller or bigger? Tell me when to stop drawing. Okay, just yell, stop! When it's time to stop drawing the force of gravity here. Now? All right, that works. Gravity is bigger than the force of air resistance. How much bigger? Don't know. But it's bigger. How'd you know that, Merrick? Not because he's falling, no. Because he's accelerating. Okay. If he was falling but slowing down as he fell downward, then it would be an upward acceleration, and then FG would be smaller. Because he's accelerating down, FG is bigger. All right. Okay, time to go here. Let's say F net equals the sum of the forces. Let's say F air. Could have just called it FA if we wanted to. Plus FG. What do I got for mass here? That's what we're trying to find, isn't it? M times negative 5.96. Hey, this is a lot like the last question. Simplify this just a little bit. Take this over to the other side by adding. It should give me a mass of 64.9 kilograms. Seems pretty reasonable, right, for a skydiver, 64.9 kilograms. little lighter than I am, but good. Sometimes we solve this and we get a mass of like 800 kilograms. Well, like, stop and think, does it make sense? It's a skydiver. Like somebody said a little while ago, Nick, I think it was, he said, the guy that had the really heavy guy that we were talking about in that other question, he's not the guy you want to be in the elevator with, right? Well, if this guy is 800 kilograms, he probably doesn't want to be skydiving, right? So is it reasonable? Right? We get an answer of 64.9. That's reasonable. Okay, that's your mass-ish, right? Roughly, give or take 10 or 20 kilograms, but roughly it's yours. It's reasonable. Okay, so it doesn't guarantee we're right, but it means we're probably right. Yep. Yep. All right, let's take a look at these two questions then, please, on page 153. Let's take a look at number 2 here, okay? It says, during a bungee jump, the velocity of the 55-kilogram woman at the lowest point is 0, and the cord stretches to its maximum. So she's jumping, she speeds up, she speeds up, she speeds up, she speeds up, and then all of a sudden the cord starts stretching. And as the cord starts stretching, what happens to her? She slows down, she slows down, she slows down, she slows down, and she stops. And then what happens? She speeds up again, but this time upwards, in the upward direction. Make sense? So she speeds up until the cord stretches, then she slows down and stops, and then she speeds up in the upward direction. All right. Compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she's accelerating due to gravity. So up here, she's accelerating due to gravity. Which way is her acceleration as she's free falling here? The cord hasn't stretched yet. Which way is her acceleration? Downward, right? Her acceleration is downward at a rate of 9.81 meters per second squared. It's as if the cord wasn't attached yet. Now, as we're going to add a little bit to this question. As she is slowing down, in other words, as the cord is stretching and she's slowing down now, which way is the acceleration? She's still moving downwards, right? But it's an upward acceleration. Even though she's moving downwards, her acceleration is upward because she's slowing down in the downward direction. What happens when she reaches the bottom? She gets to the bottom right there. She stops. Which way is her acceleration then? Upward, downward, or no acceleration? Who says up? Who says down? Who says no acceleration? Who says up again? Ben? Ben, the only one that gets this right? It's an upward acceleration. Even when she's stopped. Think about it, guys. A velocity of 0 in the equation A is equal to delta V over delta T is no different than a velocity of -3 or +4. It's just another velocity. Acceleration is not V over T. It's delta V over delta T. And as she stopped, that one brief moment that she stopped, just like that one brief moment that she's traveling at -3 meters per second downwards, her velocity is still changing because it will, one tiny fraction of a second later, be an upward velocity. So she's still accelerating. Which way is she accelerating? Well, it's an upward force that's acting on her, so it's an upward acceleration. As soon as the cord begins to stretch, it's an upward acceleration from the time it begins to stretch till the time when she's at rest at the bottom, till the time when she's being propelled upwards again by the cord. Until the cord is no longer stretched, her acceleration is a positive value. Does that make sense? All right, that's a good place to finish it up today.